everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. Welcome to my class. So, today, as you can see, the topic of today's class is DC motor characteristics. So, in my previous presentations, we have seen that what is the construction of DC machine. Then we have done the classification as per the energy input and energy output. Then we have seen what are the different types of machines we have. So from that, those things we have understood that DC machine can be act as a DC motor. At the same time, that same DC machine can be act as DC generator. So only input and output terminal, if we change, then DC motor can act as a generator, or a generator can act as a DC motor. So as we know, in case of DC generator, we have to give mechanical input and we will get electrical input, electrical output. And in case of DC motor, we will see that we can see that actually that electrical energy we have to give as input energy, and we will get mechanical energy output from that system. Now with that, we have seen that what are the working principle of that one, what are the different types of that one. So there in the types we have seen that in a DC machine, say this DC motor, we have two types of winding. What are the windings? So basically in DC motor we have two types of winding. One is the field winding, second one is the armature winding. So field winding is on the stator part, and armature winding is on the rotor part. So field winding is a stationary winding, as we know already, we have discussed all those things, and the armature winding is a rotating winding. So now in today's class we are going to see that uh, what are the different characteristics of DC motor has. So now to do the characteristics of DC motor, first of all we have to know what are the different types of DC machines we have, DC motor we have. So in DC generator also, and in the types those presentation, we have seen that a DC motor can be classified into three categories as per the field and armature winding connection. What is the connection? Those two winding can be connected in series. If both winding are connected in series, then that DC motor is known as the DC series motor. If that field winding and armature winding connected in parallel, then they are known as the shunt motor, DC shunt motor. And if with this armature, if field and armature winding with the armature field winding is connected in series parallel, both combination, then it is known as the compound. Again, compound can be classified according to the connection, that is the cumulatively compound and differentially compound in motors. So one by one we are going to discuss those things. So that means basic category of DC motor is that there are three types of motors. One is a series, second one is a shunt, and third one is a compound. So let us start with this presentation, and with that we will see that what are the different characteristics we have for the different types of motors. Let us start. Yes. So characteristics. So this slides represent the characteristics of DC motor. So what is written over here? First, let us check. Then we will go for the derivation, or the not derivation, for the characteristics. Okay. To study the performance of DC shunt motor, various types of characteristics are to be studied. So in all kind of motors, we are going to see these three kind of characteristics. First one is the torque versus armature current characteristics, speed versus armature current characteristics, speed versus torque characteristics. So for each motor, maybe that is DC shunt, DC series, DC compound, for all those cases, basically we have to know these three types of characteristics there, that is torque versus armature current characteristics, speed versus armature current characteristics, and speed versus torque characteristics. So one by one we are going to see how these characteristics are appearing. So let us do that. So this is the first characteristics where we can see that, that is the torque versus armature current characteristics of DC shunt motor. So when we have done the torque equation, so there we have seen that if we consider that for a particular motor, if we consider P, Z, so those things as constant term, then this torque is directly proportional to the I into IA into phi, that is the torque is directly proportional to the armature current, that is IA into phi. Phi is the flux of the system. Now if we are considering we are considering a shunt motor means with the source, the field winding is connected in parallel, correct? So if the resistance value of the field winding is constant, if we consider, then we can consider that the current flowing through the uh, field winding is constant, because the resistance of that field winding is constant. So if it happens, then that means we can say that flux is also constant. That means the resistance of the field winding is constant, and that's why the current flowing through the field winding will be constant. And if we are considering the current is constant in the field winding, then we can say that whatever flux is generated, that flux is also constant. And if we consider that, then we can say that in case of DC shunt motor, the torque is directly proportional to the IA, where IA is the armature current. So now considering this concept, can we draw the characteristics? Yes, we can draw. So in the below section, as we can see over here, so this is the uh, characteristics between the torque and armature current. So as you can see that it is directly proportional. That means if the armature current is increasing, torque is increasing. If armature current is decreasing, then torque is decreasing. So this is simple. It is directly proportional, provided the field current should be constant. And if field current should be constant, then the field flux will be constant. And if field flux is constant, so then torque will be, this T will be directly proportional to the armature current. Okay, so let us go to the next characteristics. Yes, speed versus armature current. So we know that the EMF equation is given by NP phi Z by 60A, and also from the KVL, applying the KVL in the DC motor loop equation, if we make, so there we can find out this EB is equal to V minus IA into RA. Okay, so from that equation, so follow my pointer. So here, as we can see, follow my pointer, speed N is equal to V minus IA RA by 5PZ into 60A. Now can we consider that 60A by 5P 60A by PZ is a constant? Yes, we can consider, as for a particular machine, the what is A? A is the parallel path, it is fixed. 60 itself, it is a constant term. P is the number of poles for a particular machine, it will be constant. Z is the total of number of conductance on the rotor, so that will be constant. So if we consider those things are constant for a particular motor, so then we can say that N varies is V minus IA RA by 5. So that will be the relation between speed and armature current, and from that equation and that relation we have to draw the characteristics. So ultimately, we are considering it is a shunt motor. So already we have discussed that in case of shunt motor, that flux is a constant term, as the shunt resistance is a constant term, constant one. So we can reduce that equation, follow my pointer. So we can reduce that equation from N varies as V minus IA RA. Okay, so for, so now in this equation, this one Vn varies as V minus IA RA. Okay, so in this equation, if we consider that we are considering an ideal armature winding, Ideal armature winding means it doesn't has any resistance value. That means RA is not present over there. That means RA is 0 over there. Now, if we do that, then what we can say? We can say that this component will be 0, correct? This component will be 0, and the speed being directly proportional to the V. Okay, correct? So so we can say that with the change of armature current, so initially when the value of current is 0, when this IA current, follow my pointer, when this IA current is 0, that means when this location for in the graph, follow that pointer, follow, this is the armature current 0. So at the time the speed has a maximum value, it is directly proportional to the terminal voltage. Now after that, when we are increasing this current value, when we increasing the current value, that difference is actually decreasing, correct? It is decreasing. So when it is decreasing, that means it will be fall. So it should be constant. It should be constant. In ideal case, it should be a straight line. That means the armature current should not have effect on this speed. But in real case, we can say that here some drops are there. Okay, so that thing is happening in this motor. Okay, so this is why this shunt motor is considered as a constant speed motor. So because here due to the change of this IA and a small change in the armature speed is occurred. Okay, so these are the different characteristics we have in case of DC shunt motor. That's why it is used for the where we need a constant speed. Okay, so coming to the next presentation. Okay, this is the next characteristics. Here we can see the speed versus torque characteristics. So there are no such equation where there is no direct relation in between speed and torque. So there is the equation where torque and armature current has a relation. There is the equation where speed and armature current has a direct relation, but there is no such equation where we have the relation in between speed versus torque. So how to do the characteristics? How we will draw the characteristics? So if we think of that how we can draw this one. So in the first characteristic, if we go back, so here we are in the first characteristics, follow my pointer, we are considering that torque is directly proportional to the IA. Okay, remember this one. Coming to the next one, so this is the next one here. So armature current is directly proportional to torque, correct? So now if we in this, follow my pointer, this is our equation, correct? So in this equation, instead of I, if we uh, put the torque, then what will happen? Because this IA is the proportional to the torque, so we can replace this here. If we can think of that instead of IA, if we have a torque, so the whatever is, so that means when this torque value is increasing, so this difference is going to be decreased. When torque, that means instead of IA, follow my pointer, instead of this IA, if we plot torque over here, so you can say that when torque value is 0, the speed has a maximum value. Now when we are changing this torque value, continuously increasing, so what is going to happen? That difference B minus T into RA, that difference is going to be decreased, and if it is decreasing, so the speed is going to be decreased. So that thing, so that's why the same characteristics appears as we have seen that in case of uh, speed versus armature current. So let us see what is written over here. For the above two characteristics of DC shunt motor, the torque developed and the speed and various armature currents of the DC motor may be noted. If these values are plotted, the graph representing the variation of speed with torque developed is obtained. The curve resembles the speed versus current characteristics, as the torque is directly proportional to the armature current. So whatever I have already told you, so that thing is it is written over here in a very gist manner. So just further remember, I have to, I have written over here, but you have to understood why the characteristics is like this. Okay, you don't have to then remember that okay that line is like that. Now why this thing is happening, so that is very important. So that concept you have to understand over here. So coming to the next, so these are the three characteristics we have done for the DC shunt motor. So that three same characteristics we are going to do for the DC series motor also. Okay, so let us see. Okay, before coming to the coming to the series motor, we have the application. I'm just in a very brief manner I have mentioned over here what are the applications of those things. So let us see what are the application. Those motors are constant speed motors. Already discussed why it is a constant motors. Hence used in application require constant speed. So that's why it is required. It is this is shunt motors are used where we need a constant speed in application ways. So like lathe machine, it is running at constant speed. Drilling machine, yes, it is running at a constant speed. Grinders, correct. Blowers, compressors. So all of the constant speed machines, rotating machines. So as you can understand that that's as the properties is concerned, that's why it is used for the constant speed, where we need a constant speed. So as we are discussing now, we are going for the DC series motor. Yes, so as you can see there is a diagram. Field winding and armature winding both are connected in series, so that's why it is a series motor, and it is supplied by some sort of source, a DC source. Okay, so here as we can this diagram is concerned. So in case of shunt motor, there the current, whatever current is coming from the supply, electrical supply, that is divided into two sections. One is the field, some current is flowing through the field winding, that is the field current, and some current is flowing through the armature winding, that is the armature current. Now in this case series motor, what is going to be happen? In case of this series motor, that a single loop is there. So as there is a single loop, that means a single current will flow. That means here the field current is equal to the um, armature current, that is equal to the line current, correct. So as a single loop is there, so we can say that all currents are same over here, correct. So now we know that field current, we know that if field current is increasing, flux is increasing. If field current is decreasing, so flux is also decreasing. That means we can say that this flux is directly proportional to the uh, uh, field current. Okay, now again this this flux is directly proportional to the field current. Now here in this particular series motor, what is field current? Field current is equal to armature current. Yes, why? Because this is a series motor, so field current is equal to armature current. So we can say that in this particular type of machine, this flux is directly proportional to the Ia, correct. So now coming to the next slide. Yes. So from the torque equation of DC motor, we have seen that torque is directly proportional to the armature current into phi. So phi into Ia. Now we are discussing, we have already discussed in the previous slide that phi is directly proportional to the Ia. Now if we replace that phi is equal to Ia in the equation, then what we will find out? Then what we can find out? We can find out that torque is directly proportional to Ia square. So follow my pointer. So this is the equation, basic equation, torque proportional to phi into Ia. Instead of this phi, now we are going to place this Ia over here. So the in case of series motor, the torque equation becomes, it is Ia square. Okay, so that means from there we can say that for a little change of armature current, the torque is highly changing. That means it has a very high starting torque. Clear? It has a very starting torque. So let us see what is the characteristics. So these are the characteristics. So I think you have got the idea that in case of this one, field current is proportional to the flux, and field current is equal to the armature current. So we can replace that flux is directly proportional to the armature current. So from the torque equation can be reduced that torque is directly proportional to Ia square. And if it is happen, then we will see now what are the characteristics we have. So again, three same characteristics we are going to do: torque versus armature current, speed versus armature current, and speed versus torque. Let us start. Okay. Torque versus armature current. So as we have seen that torque, when we have derived this torque versus armature current, so that time the equation is torque is directly proportional to the Ia square. So how the characteristics will look like? Yes, this is the characteristics looks like. So let us see what is written over here. Thus torque versus armature current characteristics begin to rise parabolically at low value of armature current, and when saturation is reached it becomes a straight line as shown. So it has two sections, so follow my pointer. This is one section where the armature current value is low, that's why it is parabolically increasing, and after saturation if we again increase this armature current, so it will increase like a straight line. Okay, so as this a little change in armature current will give effect a high change in the torque value. So this is the first characteristics. Now next characteristic, speed versus armature current characteristics. So we know already in the previous shunt motor characteristics we have seen that speed equation is given by n varies v minus Ia Ra by phi. Now in the previous characteristics what we have seen that torque is proportional to the Ia square. So if we want to write down what is Ia mathematically can we write down, if T is proportional to Ia square, so Ia is equal to proportional to the root T. Ia is equal to root T. Yes, we can write down, just we have made the root of that equation T proportional to the Ia square. So there we have made the root, so the root T proportional to the Ia. So now in this particular equation, if we place that instead of I, if we plot that root T, so what will be the characteristic? Yes, that we have to plot over here, and we have to find out the characteristics. Okay, so yes, this is the characteristics. See, it is somehow hyperbola characteristic. This one is, at as the load increases the armature current increases and the field gets saturated. Once the field gets saturated, full flux will become constant irrespective of increase in the armature current. Therefore at heavy load the speed of the DC motor remains constant. Okay, this type of DC motor has very high starting torque. So this is the characteristics of speed versus armature current. Okay, coming to the next characteristics, that is the characteristics of speed versus torque. So in the speed versus torque characteristics, so as in the shunt motor case we have discussed that there the but there is no such direct relation between speed and torque. So instead of torque we will but torque has a relation with this Ia, and this Ia has a relation with speed. So from that indirect relationship, as we have seen in the shunt motor also, here also we can find out it is somehow um, same characteristics as we have in the speed versus uh, armature current. So it is also a hyperbola, as we can see the characteristic. That means when the torque value has torque has a very low value, the speed is very high. Okay, and when it is the torque is increasing, so the speed is going to be decreased. Okay, so these are the three characteristics we have. Yes, these are the application. What are the application? It is very important to understand what is the application of this series motor. So because nowadays for nowadays, though it is all over world we are using the three-phase induction motor, but 10-15 years back all heavy lifting machines are all of DC series motor. Okay, as it has a very high starting torque, so it can carry from zero speed to some extent speed a huge load at a time. So what are the applications of DC series motor? So let us say traction, hoist and lifts, crane, rolling mills, conveyors. So where we have to carry a huge load, so there actually we use this type of, from zero speed to some speed we have to carry a high load. So there we actually use this this series motor, and that characteristics actually of that torque versus armature current characteristics, where we have seen that torque is directly proportional to the Is square. So that means a very little change in the armature current, that is proportional to the load current. So it will give a very high change in the torque value. So that's why it is used. This motors are used for those purposes. So let us coming to the next. This is the compound motors. So as we have seen that series motors has some characteristics, shunt motors has some characteristics. What are the characteristics? In case of series motors, we have seen that it has a very high starting torque. In case of shunt motor, we have seen that it has a very constant speed machine. So now can we make such a machine which has both characteristics? Yes, we can make. That is a compound motor. So where the series and parallel shunt field is there with respect to this armature winding, so that both characteristics can be achieved. Okay, so what is first say for this, let us check what is written over here. The DC motor, this DC compound motor is a combination of the series motor and the shunt motor. It has a series field winding that is connected in series with the armature, and a shunt field that is parallel with the armature. The combination of series and shunt winding allows the motor to have the torque characteristics of the series motor and the regulated speed characteristics of the shunt motor. Several versions of the compound motors are short shunt compound motors, long shunt compound motors. Then we have other cumulatively compound motors, DC motors, and then we have the differentially compound DC motors. So there are different types of compound motors. The basically the two characteristics, shunt motor characteristic and series motor characteristic, both combines together a special machine, that is the DC compound motor. Okay, that is a short shunt compound motors. So here the shunt winding is connected with that armature winding. As you can see the diagram, in both cases also series parallel both combinations are there. That is actually diagram. Coming to the next, okay, this is a short shunt cumulatively compound. Then they okay, so let us see what is the characteristics we have for the cumulatively compound DC motor. The cumulatively compound motor is one of the most common DC motors because it provides high starting torque and good speed regulation at high speed. Since the shunt field is wired with similar property in parallel with the magnetic field, adding the series field and armature field, it is called cumulative. Okay, clear why it is called cumulative? When the motor is connected in this way, it can start even with a large load and then operate smoothly when the load varies slightly. Okay, you should recall that the shunt motor can provide smooth operation at full speed, but it cannot start with a large load attached, and the series motor can start with a heavy load, but its speed cannot be controlled. The cumulatively compound motor takes the best characteristics of both series and shunt motor, which makes it acceptable for most application. Yes, this is the very important point. It is written over here. Already I have told differentially compound machines is also present over here. So let us see what is written in differentially compound. Differentially compound motor used for the same motor and winding as a cumulative compound motor, but they are connected in slightly different manner to provide slight different operating speed and torque characteristics. Okay, so this connection, as we can see, yes, in the above diagram you should notice that F1 F2 are connected in reverse polarity of the armature. Clear, make that point very clear, that F1 and F2, the field terminals, are connected in the reverse polarity. In the differentially compound um, motor, the field winding is connected so that its magnetic field opposes the magnetic field in the armature and series field. Yes, it is reversely connected, so it will, whatever flux is generated, that has a reverse case, reverse direction, so definitely it will oppose the other fluxes as the opposite direction. When the sun's field's polarity is reversed like this, its field will oppose the other fields, and the characteristics of the shunt motor are not as pronounced in this motor. That this means that the motor will tend to overspeed when the load is reduced, just like a series motor. Its speed will also drop more than the cumulatively compound DC motor when the load increases at full RPM. These two characteristics make the differentially compound DC motor less desirable than the cumulatively compound. So as you can see that cumulatively compound has the most application in the industry. So this is a long shunt. Okay, so now again we coming back to our characteristics. So that is a little concept of about differentially compound characteristics and DC compound motor and cumulatively compound DC motor. Now coming back to our characteristics, where we have the torque versus armature current, speed versus armature current, and speed versus torque. So it is very simple, to draw the characteristics of DC compound motor, because it has two property, series and shunt. So if we know the series the torque armature current characteristics of series and shunt motor, so we can draw the characteristics of compound. So like this way, if we know the series shunt motors speed armature characteristics and speed torque characteristics of both machines, series and shunt, then we can draw the characteristics of compound motor. So very simple to draw. Let us check. Yes, see, follow my pointer. This is the speed and armature current. This is the speed and armature current characteristics. See, this is it should be constant over here. This cumulatively compound, this one, this is the differentially compound. So like this way, here also this is the differentially compound, this is the cumulatively compound. So speed torque, so like this way, that means if we know the two characteristics of series and shunt, in between the say uh, in case of uh, torque versus armature current. So in case of shunt motor, what was the characteristics? It is in case of, so just simple take this example, so this for shunt motor, this is the characteristics. For series motor, the characteristics is like this, here torque is equal to, follow my pointer, torque is equal to I square. So it was, the characteristics was like this, and the shunt was like this, like a straight line equation. The torque is directly proportional to this one. So the compound characteristic will be in between that. So when there is a series and there is a shunt, so in between that we have a cumulatively compound, and as the differentially compound is opposing each other, so it has a less value. So that is in the below section, here it is. So like this way, all characteristics can be done very easily in case of the compound. So like here also speed torque, so here it should be constant like this, and two characteristics. So here it is the cumulatively compound, it is differentially compound. So just think, and take a pen and paper and over that draw figure. This is the series, this is the shunt, and in between the, definitely you can find out that in between that too we have the compound characteristics. Okay, so now this is the application. So as you can understand that it has a both property, so it will applicable where we have the both property we need: elevators, rolling mill, punches, shears, planners. So these are the application of compound motors. Okay, so differentially compound motors has some other applications. The speed of this motor increases when we increase the load, which leads to an unstable operation. Therefore, we cannot use this motor for any practical applications. Okay, so these are the all thing what we have to understand for today's class. So we have done the characteristics of series, shunt and compound motors. For three characteristics, for each case we have done the three characteristics: torque versus armature current, speed versus armature current, and speed versus torque. So this is all for today. Thank you.